Hi everyone, this video is designed to talk about the concept of transmutation. As you guys know, mutation is all about change. So in chemistry, when we talk about transmutation, we're talking about some pretty weird changes, how we can actually change the composition of the nucleus by sort of messing around with the nuclear particles themselves. And this is only possible if you have an element that is radioactive. That is to say, if you want it to occur naturally. So the very first type of transmutation that we're going to be talking about is spontaneous decay, which we also know as natural transmutation. This is a transmutation or a change in the nucleus that takes place spontaneously. It's going to happen over time, whether we try and fiddle with it or not. And for this exercise, you are going to need table N, because it's going to tell us a lot about how these types of elements like to decay. So on table N, I wanted to go through two examples. The first is looking at the isotope carbon-14. And on table N, you can see that carbon-14 is a radioactive isotope, and it decays using a beta particle. So its decay mode is beta decay. And that tells us a lot about the way that the nucleus of the carbon atom is going to change. You're going to be using this information in conjunction with the information that is contained on table O, which tells us exactly what a beta particle looks like, in order to write an equation for how the carbon nucleus naturally changes over time. So what we know from table N is that carbon-14 spontaneously gives off a beta particle, which according to table O has a mass of 0 and a charge of -1. And you can write either the E or the beta sign. If it has two options, it doesn't matter which one you pick. Pick whatever you think is prettier. I'm just going to use the E. And that's going to change the carbon-14 into something else. And to figure out what that something else is, we need one more piece of information over here on the left. What we know about this atom of carbon is that it had a mass of 14, but we also need to know its atomic number because we're going to be conserving more than just mass here. So if you flip to your periodic table, you'll see that carbon is element number 6. And so we're going to put a 6 in the lower left-hand corner here so we can figure out what element it changes into. And to finish off this equation, all we need to do is note that all these numbers up top need to be equal on the left-hand side of the equation and on the right-hand side of the equation. So right now, 14 is not equal to 0, so we need to add in a number that's going to make that a true mathematical statement. And that number should be 14. We've actually got no change in mass over this natural transmutation reaction. However, the same situation is going to be true with our bottom set of numbers. Whatever is on the left has to be equal to whatever is on the right. So right now we have a statement that says 6 equals -1, and goodness knows that's not true. The number that we need to put in here to make that a true statement is 7, because 6 equals -1 plus 7, or 7 minus 1 equals 6. All we're missing is our symbol, and that's easy to find because now we know the new nucleus's atomic number, which is 7, and if you flip to your handy-dandy periodic tables, you can very clearly see that atomic number 7 belongs to nitrogen. So nitrogen is going to be what finishes off that equation there. You can use the exact same strategy to figure out even a word equation, right? The decay of uranium-235. That's not something I know off the top of my head, so I'm going to flip to table N and find uranium-235, and I'm going to see that it decays by releasing an alpha particle. So again, table O tells me exactly what an alpha particle looks like. So I'm going to take uranium-235. I know from the periodic table by finding U that that's atomic number 92, is going to naturally decay. So it does this on its own. It releases an alpha particle, which according to table O looks just like this. Again, you can use the He or the alpha symbol. And that uranium is going to change into something new. And that something new has to make sure that our mass stays the same across the top. So 235 is equal to 4 plus 231. And the same situation has to be true along the bottom. 92 has to equal 2 plus something. That something is 90. And we can flip to our periodic table and find atomic number 90. And you're going to find it in the bottom left-hand corner of the periodic table down here as TH, or thorium. So no matter how big or how small the numbers are, you use the exact same process when you're dealing with natural transmutation, this idea of spontaneous decay. If we have a hunk of uranium sitting there, it is going to make this change over time, whether we want it to or not. This stands in contrast to artificial transmutation, where we're going to take a nucleus and we are going to make it change. That's the artificial part. We're going to force a change to this nucleus. Now, nitrogen, as we saw on the periodic table and in our previous example, has an atomic number of 7. And looking at this isotope of nitrogen, nitrogen 14, it has the same number of protons and neutrons. Now, the number of protons and neutrons doesn't have to be the same in order for a nucleus to be stable. However, it just so happens that this is a very stable atom of nitrogen. It really doesn't want to change. What artificial transmutation allows us to do is bombard it with some particle. In this case, we're going to hit it with an alpha particle, which has a mass of 4 and a charge of 2. And under the right conditions, we're going to try and make that once stable nucleus change. And now this is not something you can predict. This would have to be an equation that you were given, or maybe needing to fill in some missing masses or atomic numbers or symbols. But when this change does occur, what we end up changing it into is oxygen and what I'll call a proton on table O, or just a hydrogen nucleus. So we can actually fill in the missing blanks here without any problems. 14 and 4 is 18. So I need a total mass up top here of 18. So what's missing on this oxygen is that it must have a charge of 17. And using either the periodic table or your conservation of charge, you're going to find that the atomic number for O should be sitting at 8. And what differentiates artificial transmutation from spontaneous decay or natural transmutation are 2 key giveaways, right? The first and foremost that you should draw your attention to all the time if you're asked to pick out either spontaneous or artificial transmutation. Up here, this happened on its own. I just took 1 atom of carbon and I let it do its thing. I didn't need to add anything else on the reactant side. However, down here, I needed to hit that original nucleus with another particle. So in artificial transmutation, you will always have 2 reactants, whereas in natural transmutation, there will only be 1. Moreover, in artificial transmutation, the nucleus that you're going to see should originally be stable. Now, that's not something that you're going to know off the top of your head, but it's just a little fun fact that, yes, we have to force this transmutation to take place, so it is a non-spontaneous process. And I've talked a lot about nuclear stability here and, it's going to release a beta particle or an alpha particle naturally. Remember, folks, that stability is coming as a result of the ratio of neutrons to protons. If we have a nice, happy ratio of neutrons and protons in our nucleus, that element will be, or that isotope of that element will be stable. That doesn't mean that these 2 values have to be equal. There just has to be an appropriate number of neutrons for the number of protons that are in our nucleus. That can be 1-to-1, but it can also go up to about 1.5 neutrons per proton as we get to heavier and heavier atoms. They need more of those neutral neutron spacers to help keep those positively charged protons from pushing too hard against one another. So whether you're decaying spontaneously or artificially, transmutation is all about change of element, which is something you can only do in nuclear chemistry. It has nothing to do with electrons and everything to do with the nucleus. So keep in mind those differences between what makes something spontaneous versus what makes it artificial.